All right, welcome to the next video. Today we're going to be talking about photoelectron spectroscopy. Okay, so we're still in Unit 1, now we're on Topic 6, photoelectron spectroscopy. This is sometimes abbreviated as PES, by the way, and I'll mention that later on in the video. All right, let's get going here. So, the learning objective for this topic is for you to be able to explain the relationship between the photoelectron spectrum of an atom or ion and the electron configuration of the species, as well as the interactions between the electrons and the nucleus. Okay, so you're explaining the relationship between the photoelectron spectrum and these two things. Okay, which you will be able to do once we get through with this video. All right, table of contents for today. We're going to talk a little bit about Coulomb's law, ionization energy, the photoelectric effect, and then lastly, we'll sort of tie things together with a discussion about photoelectron spectroscopy. The problem-solving portion of the video is going to focus primarily on analyzing and interpreting photoelectron spectroscopy data. Okay, so Coulomb's law. Mr. Acampora has published some videos that go over Coulomb's law as well, so my discussion of Coulomb's law here is going to be relatively brief, and we can always go back and talk about it a bit more if we need to. So, what is Coulomb's law? So Coulomb's law is a mathematical formula, and what it does is it gives us insight into the behavior of subatomic particles in atoms, specifically protons and electrons. And Coulomb's law is actually useful in a number of other places in chemistry, which we will reference later down the road. Okay, so you should know this, right? Protons are positively charged, electrons are negatively charged, therefore they are attracted to one another. What Coulomb's law does is it gives us a formula to actually calculate the magnitude of that attraction, okay, or the magnitude of the force of attraction. What you can see here is the different items in Coulomb's law, what they mean. So F stands for the force, or the electric force. Think of that as the force of attraction. K is a constant. Okay, it's not really important what that number is right now. Q1 and Q2 represent two different charged bodies that you are referring to. So for our purposes, Q1 and Q2 are going to represent the positive charge in the nucleus and the negative charge of an electron. And then R stands for or represents the distance between those two charged bodies. Okay? So, as I was mentioning before, we're going to need to apply Coulomb's law in the future between more than just protons and electrons, but for now, let's just stick to protons and electrons, okay? So, Coulomb's law generally tells us that the magnitude of attraction between the nucleus, which contains protons, right, positively charged, the magnitude of attraction between the positively charged nucleus of an atom and its surrounding negatively charged electrons depends on two key factors, okay? Factor number one is the magnitude of charge in the nucleus. So you can think of that as being Q1, for example. Okay, so let's, for the purposes of this video, let's assign Q1 to be the charge of the nucleus, right, the positive charge of the nucleus, and we'll say Q2 is the negative charge of an electron, okay? So, the force of attraction between the nucleus and an electron is contingent upon the magnitudes of those forces, how big those forces are, and it is also contingent on, item 2 here, the distance between the nucleus and the electron, or the electrons. K, like I said before, is just a constant. That's going to be the same number each and every time. So it's not really something that changes between different situations. All right, so we don't really have to consider it, at least for today. So what does this mean? Well, when the magnitude of charge in the nucleus is larger, okay, so when Q1 is bigger, then the magnitude of attraction is going to be bigger, right? And that makes sense, right? According to what the formula says here, right? If Q1 is bigger, then F is going to be bigger, right? And then if Q1 was smaller, then F would be smaller, right? If we're like comparing situations. On the flip side, let's talk about the distance here, right? When the distance between the nucleus and electron is larger, okay, the magnitude of the attraction is going to be smaller, right? And that is because this factor here, R, or R squared, is in the denominator, right? So as the, and you guys probably understand this, right? As a nucleus and an electron get further and further apart, that distance increases, okay? And if you're dividing by a bigger and bigger number, then the force actually gets smaller, right? So as an electron moves away, or as an electron is farther and farther away from the nucleus, the force of attraction that it feels towards the nucleus is going to be smaller and smaller. It's exactly the same way that gravity works, okay? So here on Earth, we feel a certain amount of attraction to the Earth, right? Gravitational force to the Earth. But if you are many miles above the Earth's surface, you're farther away from the Earth, you don't feel quite as much of an attraction, right? So that's why spaceships can that's why things that we've launched into outer space can maintain orbit, right? The higher and higher that you get, the less and less work you need to do to actually stay above the surface of the Earth. So it's the same concept as gravity. And in fact, there is a similar equation that looks very similar to this to calculate the force of gravity. Those of you that are in physics right now will probably encounter that soon if you haven't already. Okay, so let's sort of take that information about Coulomb's law and let's just store that in the back of our heads for just a second. We're going to talk a little bit about ionization energy. And we're going to be coming back to ionization energy, but I think this is a good way for us to just apply Coulomb's law so that we get a little bit of a better handle on it. So ionization energy is the energy required to remove an electron from a gaseous atom or ion. The fact that this says gaseous is not super important, but this is strictly what the definition of ionization energy is. It can be expressed like this. Okay, so there's this little equation here. Basically what this says is that if you have some atom, when it is ionized, that atom is losing an electron, okay? And so you end up with a positively charged ion, right? If we've lost an electron, then we end up with a positively charged ion plus the electron that we lost, okay? So the ionization energy is the amount of energy required for this process to happen, okay? And the thing is, this actually can happen multiple times, right? You could take this positively charged ion that we produced here, and you could remove another electron off of it, okay? And so you can see here that this little graphic or diagram down here has 4 different ionizations taking place. These values over here, I1, I2, I3, I4, are the different ionization energies associated with these 4 different processes, okay? And as you can see, which I'm going to talk about here in just a minute, but I'll go ahead and say it now. As you can see, these ionization energies increase each time, okay? So, why the increase, right? Why do these ionization energies get larger and larger, okay? There are 2 reasons, okay? Reason number 1 has to do with Coulomb's law, okay? Coulomb's law tells us that the higher the charge, right, the bigger Q1 is, the higher the force, okay? It requires more energy to remove an electron from a positively charged aluminum ion than it does from a neutral aluminum atom, because the aluminum ion, the positively charged aluminum ion, has a higher overall positive charge than the neutral aluminum atom, okay? So it really does make sense. If you just take a look here, right? Let's look at these first 2 ionizations, right? In the first one, we have a neutral aluminum atom, which has an overall charge of 0. Okay, it's a neutral atom. The ionization energy, so the amount of energy required to pull an electron off of aluminum is 580 kilojoules per mole. By the way, this unit here, we certainly could talk about the ionization energy required to rip one electron from one aluminum atom. But oftentimes, ionization energies are given in units of energy per mole. So, because I mean, how often are you actually going to be working with a single atom of aluminum? The answer is never, okay? So, but you could be working with a mole of aluminum, right? Or multiple moles. So, ionization energies are usually given in units of energy or joules per mole. So, back to what I was saying. The amount of energy it requires to take an electron away from a neutral aluminum atom is only 580 kilojoules per mole. However, if you try to do this again, right, take that positively charged aluminum ion and try to rip another electron away from it, it becomes much harder. Okay, and that is because two reasons. First reason, which I'm talking about now, is that this aluminum ion is positively charged. So we have a greater overall positive charge here that is binding that second electron more strongly, right? The force of attraction is literally stronger in this situation, and so it requires more energy to take that electron away. Okay, that is one of two reasons. Now the second reason is, I think, a little bit more interesting, and maybe a little bit easier to understand. So the second reason has to do with the energies of the electron orbitals. Okay, so let's consider the electron configurations in play here. So I have the electron configuration of the neutral aluminum atom, okay, 1s2, 2s2, 2p6, 3s2, 3p1. And then I have the electron configuration of the positively charged aluminum ion. This is the exact same thing as this, except we've taken this electron away, right? So like we've removed that first electron, and so this 3p1, this one electron here in the 3p orbital, that's gone now. Okay, so we have this electron configuration. So let's consider in each of these scenarios which electron is getting removed. So in the first situation, it's this electron right here, the electron that's in the 3p orbital. Okay, in this situation, the electron that's being removed is in the 3s orbital. Okay, according to the quantum mechanical model of the atom, electrons in the 3p orbital are higher in energy than electrons in the 3s orbital, aka when it says higher in energy, it means that they're easier to take away. Like, let me put this, think about it in terms of gravity again, right? So if there's a satellite that's orbiting the Earth at some large distance, right, and then there's, you sitting on Earth, it would be a lot easier to just sort of flick that satellite away, because it's not very tightly bound to the Earth, than it would be to completely remove you from Earth, right? You'd have to get launched out of Earth, and it'd take a lot of energy to do so. Same kind of concept here, okay? These orbitals are in order based on their energy level, right, or the amount of energy, okay? And so the further away, or the higher the energy of the electrons, the easier it is for them to be removed. Okay, so take that information about ionization energy and just put it off to the side for a moment, okay? What I'm going to do now is I'm going to talk about the photoelectric effect. And we actually talked about the photoelectric effect last time without us actually really knowing, okay, that we were talking about it. So I just want to remind you guys of these two diagrams here. Okay, so let's just remember a few things before we move on. This is the line spectra of hydrogen. Okay, so remember that when an atom of hydrogen is exposed to energy, it produces only these certain colors of light, right? And Bohr interpreted that as meaning that atoms must have specific energy levels, and the electron specifically must exist in these specific energy levels. The way that these different lines are produced is by electrons falling from one specific energy level to another, and those distinct amounts of energy that they lose correspond to the distinct wavelengths of light and colors of light that we observe in the line spectra. So this process, okay, is called the photoelectric effect. And when I say process, I mean it's the phenomenon of electrons being emitted from substances, okay? And so take a look at this diagram here. This is another way to sort of think about the photoelectric effect, all right? What actually happens in reality is this, okay? So if you have a metal surface, okay, if you shoot low frequency or low energy light at that surface, nothing will happen, okay? In this specific example, nothing will happen. However, if you shoot high frequency or high energy light at the surface, electrons come off the surface. They're emitted from the metal, okay? This is a experiment that was done by, I'm sure, several scientists, most notably Albert Einstein. He spent some time looking at the photoelectric effect. And the implications of this are really interesting, okay? So you've got some low frequency light that does nothing. Then you have some high frequency light that does something, okay? It causes electrons to be emitted from the metal surface. What this means, okay, and I summarize this here in this last little blurb, what this means is that there must be somewhere in the middle where there is a minimum frequency or a minimum energy where this exactly starts to happen, okay? There must be some minimum frequency or minimum energy required to free an electron from the atoms, which make up the surface of the metal. You see what I'm saying? Think of it as almost like you have like a dial, right? And you could sort of crank up the frequency or the energy, right? And you could measure, and you were like looking to see if the electrons were coming out, and you keep turning it up, and you keep turning it up, and you keep turning it up, and then all of a sudden, boom, it starts happening, right? That would be the moment, or that would be the minimum frequency that's required to free the electron from the atoms of the metal, okay? So let's try to put this all together, okay? I'm trying to make this video not as long as my previous ones, so I apologize if I'm going through things quickly. But let's try to put all this stuff together, okay? So what we just saw was a little summary of the photoelectric effect, right? Essentially what's going on here is electrons can be emitted from atoms if they're given enough energy, okay? If they're given enough energy from electromagnetic radiation. And we also spent some time talking about ionization energies, right? Which has to do with electrons coming off or being removed from atoms, okay? So let's try to put this stuff together, all right? I'm going to ask you a question, and what I'd like you to do, seriously, is pause the video when I ask the question. I'm not going to pause, I'm just going to go on with the answer. But what I'd like you to do is I'd like you to think about it at home, okay? So here's the question. Ionization energy, right, which is the amount of energy required for an electron to be removed from an atom. The question is, how are ionization energies measured? Okay, how do scientists obtain numbers like this, right? This has all of the different ionization energies for all of these different elements. How do we get this, right? So take a moment to pause the video and see if you can think about how ionization energies might be measured. Okay, so how on earth could this happen? Well, let's think about it, right? If we can use this idea of the photoelectric effect, right? Think of like what I was talking about before, right? Having a dial, right? If we could dial up the amount of frequency, right, that we're shooting at a metal surface, if we could turn that up, and if we could notice exactly when the electrons start being emitted, then we could look at our dial and we could say, oh, it's right here, right? This energy or this frequency that I'm using right here will cause electrons to leave. Not before that, right? Because we have to stop the dial as soon as it happens for the first time. And so that is essentially how ionization energies are measured, okay? This process is called photoelectron spectroscopy. Okay, it's a technique, like I said, it's abbreviated PES. Okay, and what this does is it enables us to not only measure the ionization energies of electrons in an atom, but it enables us to determine the relative energies of all the electrons in an atom. Okay, so it's not just like the first electron or the second electron. You can do this for like all of the electrons in an atom. Okay, I'm not going to get into the nitty-gritty details of this. You can read about this on page 287, 288 in your book. But basically, what scientists do is they shoot really, really high energy photons at, and photons are just packets of electromagnetic energy, shoot really high energy photons at a sample, and the kinetic energies of the ejected electrons are measured. So it's not quite like what I was describing before, where they take a dial and they like slowly crank it up. Okay, what they do is they just take the highest energy photons or the highest frequency photons they've got, and they just blast it at the sample, and they do a little bit of clever math with the electrons that get ejected to essentially come up with the energies for each of the electrons that they're observing. Okay. I'm going to go into some more detail on this equation here in the problem-solving version of the video. What I'd like to do now is show you some data that you actually can get from photoelectron spectroscopy. Okay, so photoelectron spectroscopy produces graphs that kind of look like mass spectroscopy graphs. Right, this might look a little bit similar to something we looked at a few weeks ago. So let's try to interpret this, okay? And this is my last slide for today, or the second to last slide, I think. So we're almost done. As you move from left to right, what we're seeing is that different peaks occur, right? And these peaks represent numbers of electrons. We're seeing different peaks at different amounts of energy, okay? And it's decreasing energy, all right? So like here we've got the most energy and here we've got the least. The first peak corresponds to the highest energy orbital in the atom, which would be the 1s orbital, right? And the next peak would be the next highest energy, okay, which would be the 2s orbital, and it sort of goes on from there, all right? The magnitude of the peaks indicate the relative number of electrons, okay? So as you can see, all of these s orbitals have roughly the same height, okay? We can interpret that to mean that they all contain 2 electrons, right? Because s orbitals can hold 2 electrons. And we know that like if we have electrons over here, that means we definitely have electrons in the 1s and 2s orbitals. And so if this height is the same as this height is the same as this height, then all 3 of those must have the same number of electrons, and so they all have 2, right? Same thing can be said for the other types of orbitals. However, if we look at what we actually have here, right, the data that came out of the photoelectron spectrometer, we see that we have a really tall 2p peak and a not so tall 3p peak. Okay? If I have electrons over here, that means that this orbital should be full, right? So I'm going to go ahead and assume that this means that I have 6 electrons in the 2p orbital. And if you look at the relative heights between like 2s and 2p, for example, seems reasonable, right? If you multiplied this peak by 3, right, 2 times 3 would be 6, you'd get a peak that's about this high, right? So it's safe to assume that the 2p orbital has 6 electrons in it. But what about the 3p orbital? This one's a little bit tougher. Well, I can say 2 things for sure, right? Number 1, it's not as big as the 2p peak. So there are not 6 electrons here. Okay, I am very confident in that. The other thing that I can say is that it is bigger than the 3s peak, right? I mean, the 3s peak is down here, and the 3p peak definitely comes higher than that, right? It's a significant distance above that. Not by a lot, but it's definitely different height than the 3s orbital. So I'm interpreting this to mean that perhaps there's 3 electrons here, right? Maybe it's just 1 more than 2. Right, and honestly, if you were to like multiply this peak by 2, right, you would probably end up with a peak that's about this size, right? So 3 times 2 would be 6. So that tends to match up. What you can do then, right, if you take a look at this photoelectron spectra, what you can do is you can come up with the electron configuration for this element or for this substance, right? So keep in mind, scientists, let's say you don't know what the sample is, right? You put some sample into a photoelectron spectrometer, you get data like this, and you want to try to use this data to figure out what the sample is, right? Well, if you get this data, you count up the total number of electrons, and you know where those electrons are, then you can figure out what element it is, right? You see there at the bottom. The electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p3. Add up those electrons, 15 electrons, okay? Assuming this is a neutral substance, that would be phosphorus, okay? So that's one way that scientists can go about figuring out what a sample is or what a substance is using a photoelectron spectrometer. Okay, that is the video for today on the content. Like I said, the problem-solving video is going to go into a bit more detail on some of the math, and then also some other scenarios that you might see in some data interpretation. Okay, thanks a lot for watching.